In the vast, unfathomable reaches of space, there are mysteries so profound that they leave us in awe, wondering about the origins and the very fabric of our universe. Among these mysteries is a remarkable relic of the earliest moments of creation, the cosmic microwave background, CMB. Often referred to as the afterglow of the Big Bang, the CMB is the oldest light in the universe, a silent yet powerful echo that gives us a window into the birth of everything we know. This discovery not only reshaped our understanding of the cosmos but also led to more questions than answers, making it one of the most intriguing puzzles in the study of space. But before we continue, if you like this type of videos, please subscribe to the channel and comment. Imagine this. At the very beginning of time, the universe was a dense, hot, and incredibly compact ball of energy. A fraction of a second after the Big Bang, the universe began expanding and cooling rapidly. During those early moments, the universe was opaque. Radiation could not travel freely because the charged particles were constantly interacting with photons, the particles of light. But about 380,000 years after the Big Bang, something remarkable happened. The universe had cooled enough for electrons and protons to combine and form neutral atoms, allowing light to travel freely for the first time. That light, stretched over billions of years as the universe continued to expand, is what we now detect as the cosmic microwave background. The story of the CMB's discovery begins in the mid-20th century, and it involves both a mix of serendipity and scientific curiosity. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, using a large horn antenna for satellite communications experiments. They weren't expecting to stumble upon one of the greatest cosmological discoveries of the century. Their goal was far more mundane: to eliminate any background noise from their antenna system. However, no matter how much they fine-tuned their equipment, they were constantly met with a strange, persistent noise, a faint hum that came from all directions. Initially, they thought it was interference from nearby cities or maybe even pigeon droppings on the antenna. Yet, after removing all possible sources of contamination, the noise remained. Penzias and Wilson had unknowingly detected the cosmic microwave background, the faint radiation that permeates the entire universe. This hum, this ever-present signal, was the lingering heat from the Big Bang itself. Their accidental discovery provided evidence that confirmed the Big Bang theory, which had been postulated by scientists such as Georges Lemaitre and Alexander Friedman decades earlier, but had lacked direct observational support until then. What makes the CMB so captivating isn't just that it confirms the Big Bang. It's what this ancient light reveals about the early universe and the fundamental laws that govern it. When scientists first began studying the CMB in detail, they found that it wasn't uniform. Although the radiation is almost the same in every direction, there are tiny fluctuations in temperature, minute differences in the energy levels. These fluctuations, while incredibly small, on the order of 1 part in 100,000, are a cosmic goldmine of information. They represent the seeds of the large-scale structures in the universe today: galaxies, stars, and clusters of galaxies. By studying these fluctuations, scientists can piece together a picture of how the universe evolved from a hot, dense plasma to the structured, complex cosmos we observe today. One of the most fascinating revelations from the CMB is that the universe is flat. Not in the sense of being two-dimensional, but in terms of its geometry. If you imagine space as a three-dimensional grid, its curvature can be either positive, like a sphere, negative, like a saddle, or flat, like a sheet of paper. By analyzing the patterns in the CMB, particularly the size of the temperature fluctuations, scientists discovered that the universe is incredibly close to being perfectly flat. This has profound implications for cosmology because it supports a theoretical model known as inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. Inflation theory explains why the universe appears flat and why regions of the universe that are now widely separated have similar properties, even though they should not have been in contact with each other in the early universe. The CMB has also helped scientists pinpoint the age of the universe with remarkable precision. Before its discovery, estimates for the age of the universe varied widely. However, by studying the CMB and combining it with observations of the expansion rate of the universe, known as the Hubble constant, cosmologists have determined that the universe is about 13.8 billion years old. This level of accuracy would have been unimaginable just a few decades ago. Yet, the CMB is not without its mysteries. One of the most puzzling aspects is something known as the cold spot. This region of the CMB is unusually colder than its surroundings, and while scientists have proposed various explanations, from statistical anomalies to large-scale cosmic structures like supervoids, the cold spot remains an enigma. Some have even suggested that it could be evidence of something more exotic, such as the imprint of another universe interacting with ours in the distant past. This, of course, is highly speculative, but it demonstrates how the CMB continues to provoke new questions and push the boundaries of our understanding. Another mystery related to the CMB is the so-called axis of evil. When scientists analyzed the CMB data, they noticed that the fluctuations weren't entirely random. Instead, there appeared to be a strange alignment in the way certain patterns were distributed across the sky. This was unexpected, as the standard cosmological model predicts that the universe should be isotropic, meaning that, on large scales, it should look the same in every direction. The alignment of the CMB fluctuations has led some researchers to wonder if there's a deeper underlying structure to the universe, something that challenges our current models. The precision with which we can now study the CMB has opened up entire new fields of research. For instance, scientists are using the CMB to investigate the nature of dark matter and dark energy, the two mysterious components that make up about 95% of the universe. Dark matter doesn't emit light or radiation, making it invisible to telescopes, but its gravitational effects can be observed in the way galaxies move. By studying how the CMB was affected by dark matter in the early universe, scientists can learn more about its properties and distribution. Similarly, dark energy, which is driving the accelerated expansion of the universe, leaves subtle imprints on the CMB. Although we still don't fully understand what dark energy is, the CMB provides clues that could eventually lead to its discovery. The study of the CMB also allows scientists to peer back to a time before stars and galaxies even existed, to a period known as the Dark Ages of the universe. This was a time when the universe was filled with neutral hydrogen atoms, and no light could be emitted. However, the slight temperature variations in the CMB offer insights into the conditions that eventually led to the formation of the first stars and galaxies, marking the end of the Dark Ages and the beginning of cosmic reionization. In recent years, advancements in technology have allowed for even more detailed observations of the CMB. The Planck satellite, launched by the European Space Agency in 2009, provided the most precise map of the CMB to date. Its data has not only refined our understanding of the universe's age and composition, but also helped to confirm the theory of cosmic inflation with greater confidence. Planck's observations have shown that inflation likely occurred at energies far higher than anything we can recreate in particle accelerators on Earth, giving us a glimpse into physics at its most extreme. But even with all of these discoveries, there are still many unanswered questions about the CMB. For example, we don't yet fully understand the nature of the initial conditions that led to the Big Bang. While inflation theory provides a compelling explanation for many features of the CMB, it's not without its challenges. Some alternative models propose that the Big Bang wasn't the beginning of everything but rather a transition from a previous cosmic phase or even a previous universe. These ideas are highly speculative, but they show just how much we have yet to learn. The cosmic microwave background is one of the most important discoveries in modern cosmology, and it continues to be a source of inspiration and intrigue for scientists and the public alike. Its faint whispers from the dawn of time have helped us piece together the story of the universe, from its fiery beginnings to its expansive present. And yet, as we continue to study this ancient light, it raises new questions that drive us to explore even deeper mysteries of the cosmos. As we continue to unravel the secrets embedded within the cosmic microwave background CMB, it becomes clear that this ancient light serves as a cosmic blueprint, revealing the intricate patterns that have shaped the universe from its very birth. These seemingly faint imprints provide profound insights into the early universe and offer clues to some of the most elusive and fundamental questions in physics and cosmology. One of the central themes emerging from the study of the CMB is how it encapsulates the delicate balance of forces and conditions that have allowed our universe to evolve into its current state. The study of CMB fluctuations, for example, gives us a better understanding of the universe's early composition. Shortly after the Big Bang, the universe was a seething mixture of matter, radiation, and energy. The tiny temperature variations in the CMB map correspond to regions of slightly different densities. These differences are crucial because they represent the primordial clumps of matter that, under the influence of gravity, eventually grew into the stars, galaxies, and galaxy clusters we see today. The distribution and amplitude of these fluctuations are consistent with a universe dominated by dark matter and dark energy, giving us a strong indication of the proportions of these mysterious substances in the cosmos. One of the most compelling aspects of the CMB is its role in confirming the theory of inflation, which proposes that the universe underwent an extremely rapid expansion in the first fraction of a second after the Big Bang. This theory helps explain why the universe appears so uniform on large scales and why regions of the universe that seem to have no causal connection, because they are too far apart to have interacted via the speed of light, nonetheless have nearly identical properties. Inflation stretched the universe so quickly that small quantum fluctuations in the energy field responsible for inflation were also stretched to cosmic scales, creating the tiny temperature fluctuations observed in the CMB. However, inflation itself remains one of the great unsolved mysteries of cosmology. While the CMB provides compelling evidence for its occurrence, we still don't know exactly what triggered inflation or what the underlying mechanism was. Some models suggest that inflation was driven by a hypothetical particle called the inflaton, which decayed after inflation ended, releasing the energy that filled the universe with radiation and matter. But the true nature of the inflaton remains elusive, and efforts to detect any direct evidence of inflation, such as through gravitational waves, have so far come up short. Yet, the search continues, with the hope that future experiments will shed more light on this enigmatic period in cosmic history. The CMB also reveals something extraordinary about the fate of the universe. As mentioned earlier, the discovery that the universe is flat is a critical clue to its overall structure and destiny. In a flat universe, the balance between the expansion caused by the Big Bang and the gravitational pull of matter and energy is finely tuned. This suggests that the universe will continue to expand forever, but at an ever-slowing rate. However, the discovery of dark energy complicates this picture. Dark energy, which makes up about 70% of the universe, seems to be driving the accelerated expansion of the cosmos. This means that instead of slowing down, the universe's expansion is actually speeding up, and this has profound implications for its ultimate fate. In a universe dominated by dark energy, the cosmos will continue to expand at an accelerating rate, causing galaxies to drift farther and farther apart. Eventually, distant galaxies will recede beyond the observable horizon, leaving us in a lonely and empty universe, with only the remnants of our local galactic group remaining visible. This bleak future, sometimes referred to as the Big Freeze, is just one of several possible outcomes for the universe. While the CMB provides valuable clues to the universe's past, it also hints at this long and uncertain future. The study of the CMB is not just a triumph of observational cosmology, it is also a testament to human ingenuity and persistence. The process of extracting meaningful information from the CMB is incredibly complex, requiring highly sensitive instruments, sophisticated data analysis techniques, and an understanding of the various sources of noise that can contaminate the signal. The CMB is not a pristine signal. It is affected by many other factors, such as the radiation from our own galaxy, intergalactic dust, and even the motion of our solar system through space. Scientists have had to develop clever ways to filter out these sources of interference in order to isolate the true CMB signal. One of the key tools used to study the CMB is a technique called polarization analysis. In addition to measuring the temperature of the CMB, scientists also study its polarization, the way the light waves are oriented. Polarization patterns in the CMB are produced by interactions between photons and the plasma of the early universe, and they carry additional information about the conditions during that time. In particular, scientists are looking for a specific type of polarization pattern called B modes, which could be a direct signature of gravitational waves from the inflationary period. Detecting B-mode polarization would provide a smoking gun for inflation and offer new insights into the physics of the early universe. Although there have been tantalizing hints of B-modes in some experiments, such as the BICEP 2 experiment in 2014, the results were later shown to be contaminated by galactic dust, and the search for a definitive detection continues. The quest to understand the CMB has also led to groundbreaking advancements in technology. Instruments like the COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and Planck satellites have revolutionized our ability to study the cosmos. Each of these missions has progressively improved our knowledge of the CMB, providing ever more detailed maps of the early universe. The Planck satellite, for instance, was able to measure the temperature fluctuations in the CMB with unprecedented precision, down to scales of a few arcminutes, a tiny fraction of a degree in the sky. This level of detail allows scientists to refine their models of the universe's composition, geometry, and evolution, making the CMB one of the most powerful tools in cosmology. But despite the immense progress made in understanding the CMB, it still holds many mysteries. For instance, while the standard model of cosmology, the lambda cold dark matter model, fits the CMB data remarkably well, there are small anomalies that continue to puzzle scientists. One such anomaly is the so-called hemispherical asymmetry, where one half of the sky appears to have slightly different properties than the other. This is unexpected because the universe should be isotropic on large scales, meaning it should look the same in all directions. Some have speculated that this asymmetry could be a sign of new physics beyond the standard model, perhaps even related to the multiverse hypothesis, where our universe is just one of many in a vast cosmic landscape. Another intriguing puzzle is the low multipole anomaly, which refers to the fact that the largest scale fluctuations in the CMB are weaker than predicted by the standard model. This could be a statistical fluke, or it could point to some new phenomenon that we have yet to understand. In either case, these anomalies remind us that the universe is still full of surprises, and the CMB continues to challenge our understanding of the cosmos. As we look to the future, new experiments and missions are being designed to probe the CMB in even greater detail. The next generation of CMB experiments, such as the Simons Observatory and CMBS-4, will provide even more precise measurements of the CMB's temperature and polarization, potentially unlocking new insights into the nature of dark matter, dark energy, and inflation. These experiments will also search for subtle imprints of primordial gravitational waves, which could offer a direct glimpse into the physics of the universe's earliest moments, when space and time themselves were being shaped by quantum processes. In the grand scheme of cosmic history, the CMB represents a brief but crucial moment, a snapshot of the universe as it transitioned from an opaque plasma to the transparent cosmos we see today. It is a window into a time before stars, galaxies, or even atoms had formed, when the universe was still young and full of potential. The light from the CMB has traveled for billions of years, crossing vast expanses of space to reach us, carrying with it the story of our origins. Yet, for all that the CMB reveals, it also leaves us with profound questions. What came before the Big Bang? What triggered inflation, and what was the universe like during that time? Is the CMB the final relic of a single universe, or does it carry the imprints of interactions with other universes in a multiverse? As we continue to study this ancient light, we may find answers to these questions, or we may uncover even deeper mysteries that challenge our understanding of reality itself. The cosmic microwave background is a testament to the power of human curiosity and the endless pursuit of knowledge. It shows us that even in the vast emptiness of space, there are hidden clues waiting to be discovered, clues that can unlock the secrets of the universe and our place within it. And as we continue to gaze into the depths of the cosmos, we are reminded that the universe is not just a collection of stars and galaxies, but a living history, written in the light that has traveled across time and space to reach us. The journey of understanding the cosmic microwave background (CMB) is not only a deep dive into the mysteries of the universe but also a reflection of the incredible progress we've made in our quest to decode the cosmos. The CMB, in many ways, serves as a cosmic Rosetta Stone, translating the seemingly chaotic aftermath of the Big Bang into a coherent narrative that helps explain the evolution of the universe. However, the story it tells is far from complete. As we probe deeper, more questions emerge, each more tantalizing than the last. One of the most profound questions centers around the concept of cosmic inflation. As mentioned earlier, inflation theory posits that the universe expanded exponentially in the tiniest fraction of a second after the Big Bang, smoothing out any irregularities and setting the stage for the universe we see today. The evidence for inflation is woven into the fabric of the CMB, but while the theory solves many of the universe's problems, it also raises new ones. What drove this incredible expansion? Was it caused by a specific field, particle, or energy type? And if inflation ended, why did it stop? The most popular explanation involves a scalar field, sometimes referred to as the inflaton, which powered inflation by storing enormous amounts of potential energy. As the universe expanded, this energy was released, allowing inflation to end and giving rise to the particles, radiation, and structures we observe today. However, despite its theoretical elegance, the inflaton field remains a hypothetical construct, with no direct observational evidence. Some physicists have proposed that the detection of primordial gravitational waves, ripples in space-time produced during inflation, would provide direct evidence for the inflationary model. These waves would leave their imprint on the CMB in the form of specific polarization patterns, namely, B-mode polarization. The search for these elusive gravitational waves has been one of the central focuses of modern cosmology. The BICEP-2 experiment, which initially claimed to have detected such signals in 2014, brought immense excitement to the scientific community. However, subsequent analysis revealed that much of the signal detected was due to galactic dust rather than primordial gravitational waves. Despite this setback, the pursuit continues with more advanced instruments, such as those on board the upcoming Simons Observatory and CMBS-4, designed to tease out these faint imprints from the cosmic noise. Gravitational waves, if detected in the CMB, would revolutionize our understanding of the early universe and provide direct insight into the nature of inflation. They could offer clues about the fundamental forces that shaped the cosmos in its infancy, possibly leading us toward a unified theory of physics that links quantum mechanics with general relativity. The mere possibility of such a breakthrough keeps scientists driven and hopeful that the answers may lie just beyond the next experiment. But while inflation theory offers a compelling explanation for many aspects of the universe, some researchers have proposed alternatives that challenge this narrative. One such alternative is the cyclical universe theory, which suggests that the universe undergoes endless cycles of expansion and contraction, with each Big Bang followed by a subsequent Big Crunch. In this model, the CMB would be the leftover radiation from the most recent cycle, and the next cycle would be set in motion by the collapse of the current universe. Proponents of this theory argue that it offers an elegant way to avoid the need for an initial singularity, a point of infinite density and temperature at the very beginning of time. The cyclical model also posits that inflation may not be necessary to explain the universe's large-scale structure. Instead, the universe's current expansion is seen as part of a repeating process, where each cycle resets the cosmic clock. While this theory remains speculative and lacks the observational support that inflation theory enjoys, it is a reminder that the CMB could hold the key to multiple interpretations of the universe's evolution, each as fascinating as the next. Another speculative avenue of research looks at the CMB in the context of the multiverse hypothesis. In this framework, our universe is just one of many, each with its own physical laws and constants. The CMB could contain subtle clues that our universe has interacted with others in the multiverse. Some cosmologists have suggested that anomalous features in the CMB, such as the hemispherical asymmetry or cold spots, could be evidence of such interactions, where universes collide or imprint upon one another. One of the most intriguing features of the CMB is the so-called cold spot, a region of the sky where the temperature of the CMB is unusually low. This anomaly has puzzled scientists for years, as it doesn't quite fit the predictions of the standard model of cosmology. Some have proposed that the cold spot could be a statistical fluke, while others have suggested more exotic explanations, such as the presence of a supervoid, an immense region of space with fewer galaxies than average. But perhaps the most daring hypothesis is that the cold spot is evidence of a collision with another universe in the multiverse. According to this idea, our universe may have brushed up against a neighboring universe early in its history, leaving behind this distinct mark in the CMB. The multiverse theory, while speculative, has captured the imagination of both physicists and the public alike. It opens up the possibility that the CMB is not just a record of our universe's history, but a window into a much larger and more complex cosmic landscape. If true, the multiverse would redefine our understanding of reality, suggesting that the universe we inhabit is just one of countless others, each with its own unique properties. Beyond these speculative theories, the CMB continues to offer practical insights into the makeup and behavior of the universe. One of the most important contributions of CMB research is its ability to constrain the cosmological parameters that describe the universe's composition, expansion rate, and overall geometry. For example, the precise measurements of the CMB by the Planck satellite have allowed scientists to determine that ordinary matter, the stuff that makes up stars, planets, and everything we see, accounts for just 5% of the universe. The rest is composed of dark matter, about 25%, and dark energy, about 70%. Dark matter, which does not interact with light or other electromagnetic radiation, is thought to form the scaffolding upon which galaxies and galaxy clusters are built. The slight density fluctuations seen in the CMB are believed to correspond to regions of higher dark matter concentration, which eventually led to the formation of cosmic structures. Although dark matter has yet to be directly detected, its gravitational effects are clearly visible in the large-scale structure of the universe and the motion of galaxies within clusters. The CMB provides further evidence for its existence, as the observed pattern of temperature fluctuations matches what would be expected in a universe dominated by dark matter. Dark energy, on the other hand, remains even more mysterious. First discovered through observations of distant supernovae in the late 1990s, dark energy appears to be responsible for the accelerated expansion of the universe. While the CMB does not directly reveal the nature of dark energy, it plays a crucial role in refining our understanding of its effects. By studying how the universe's expansion has changed over time, scientists can use the CMB to place constraints on dark energy's properties and its influence on the overall evolution of the cosmos. In addition to dark matter and dark energy, the CMB provides insights into the so-called baryon acoustic oscillations, which are the regular, periodic fluctuations in the density of the visible baryonic matter, the normal matter composed of protons and neutrons, of the universe. These oscillations were set in motion by sound waves that propagated through the hot plasma of the early universe. As the universe cooled and became transparent, these oscillations were frozen into the large-scale structure of the universe. By studying the pattern of these oscillations in the CMB, scientists can gain a better understanding of the distribution of matter in the universe and how it has evolved over time. The CMB is also a key tool in measuring the Hubble constant, which describes the rate of expansion of the universe. However, recent measurements of the Hubble constant using the CMB have led to a growing tension with measurements made using more local methods, such as observing the distances to nearby galaxies. This discrepancy, known as the Hubble tension, has sparked intense debate within the cosmological community, as it suggests that there may be something missing from our current understanding of the universe. Some researchers have proposed that this tension could be resolved by modifying the standard model of cosmology, perhaps by introducing new forms of dark energy or interactions between dark matter and ordinary matter. Others argue that it could be the result of systematic errors in one or both sets of measurements. Regardless of the cause, the Hubble tension is a reminder that even with the wealth of information provided by the CMB, there is still much we don't understand about the universe's expansion and evolution. As we delve further into the study of the CMB, it becomes clear that this faint glow from the early universe is far more than just an afterglow of the Big Bang. It is a cosmic messenger, carrying with it the secrets of the universe's infancy, its composition, and its future. It challenges us to rethink our assumptions about the nature of reality, and invites us to explore new and exciting possibilities, from the existence of other universes to the true nature of dark matter and dark energy. The cosmic microwave background (CMB) has become an indispensable tool in our understanding of the universe, unlocking mysteries of both the distant past and the universe's future. The ongoing research into the CMB continually sharpens our picture of how the universe began, what it is made of, and how it will evolve. This relic from the Big Bang, frozen in time, gives us a view of the universe at its infancy, while at the same time, it provides clues to phenomena that are still elusive today, such as dark energy, dark matter, and the universe's ultimate fate. One of the most important revelations the CMB offers is a glimpse into the universe's flatness. From detailed CMB measurements, particularly those from the Planck satellite, we can infer the geometry of the universe. The evidence suggests that the universe is nearly flat, which is consistent with the predictions of inflation theory. In cosmology, the shape of the universe depends on its overall energy density. If the density is above a certain critical value, the universe is closed and curved like a sphere. If the density is below this critical value, the universe is open and shaped like a saddle. A flat universe, on the other hand, exists when the density is exactly at the critical value. The CMB's pattern strongly suggests that the universe is flat within a very narrow margin of error, confirming one of the fundamental predictions of inflationary cosmology. However, the idea of flatness raises even more profound questions. If the universe is indeed flat, how did it arrive at such a perfect configuration? Without the rapid expansion provided by inflation, a flat universe seems incredibly improbable. Without inflation, small deviations in density in the early universe would have caused it to either collapse in on itself or expand too quickly for galaxies, stars, and planets to form. Inflation explains this apparent fine-tuning by proposing that the rapid expansion smoothed out any irregularities and flattened the universe. But why inflation occurred in the first place, and what drove it, remains an open question. Additionally, one of the more perplexing discoveries related to the CMB is the existence of what's known as the axis of evil. This term refers to an unusual alignment of large-scale temperature fluctuations in the CMB that seem to defy the randomness predicted by the standard model of cosmology. Normally, the temperature variations in the CMB should be distributed equally across the sky, reflecting the random nature of quantum fluctuations in the early universe. However, researchers have noticed that certain large-scale patterns in the CMB appear to be aligned with the plane of our solar system, a phenomenon that should not occur if the universe's large-scale structure is random and isotropic. This strange alignment has been dubbed the axis of evil, and it has led some scientists to question whether our current models of the universe are missing something fundamental. There are several hypotheses to explain the axis of evil, ranging from observational biases to exotic physics. Some researchers suggest that this anomaly might simply be a statistical fluke, a rare chance alignment that only appears significant due to the limited data we have. Others speculate that the alignment could be evidence of new physics, such as interactions between the early universe and another universe in the multiverse, or an indication that the universe has a preferred direction, contradicting the cosmological principle that the universe should look the same in all directions. More research is needed to determine the significance of this anomaly, but it is a reminder that the CMB, while deeply informative, may still be holding on to secrets we have yet to fully unravel. The CMB also serves as a window into one of the most mysterious periods in cosmic history, the epoch of reionization. After the universe cooled and neutral atoms began to form, the universe entered a period known as the Cosmic Dark Ages, when the first stars and galaxies had not yet formed, and the universe was filled with neutral hydrogen. However, at some point, ultraviolet light from the first stars and galaxies began to reionize the hydrogen gas, ionizing it once more and making the universe transparent to radiation. This epoch of reionization marks the end of the Cosmic Dark Ages and the birth of the first galaxies and clusters of stars. The exact timing and nature of the epoch of reionization are still uncertain, but the CMB offers clues. The CMB photons we observe today have traveled through this reionized gas, and their interactions with free electrons during this period leave subtle imprints on the polarization of the CMB. By studying these polarization patterns, scientists can estimate when reionization occurred and how it progressed. Current estimates suggest that reionization began about 400 million years after the Big Bang and was mostly complete by around 1 billion years. However, there is still much to learn about this critical phase in the universe's evolution, and future CMB measurements, combined with observations of distant galaxies, will help to refine our understanding. The epoch of reionization is just one of the many chapters in the universe's history that the CMB helps to illuminate. Another important period that the CMB sheds light on is the formation of the first large-scale structures in the universe. The temperature fluctuations in the CMB correspond to slight differences in the density of matter in the early universe, and these density fluctuations provided the seeds for the formation of galaxies, galaxy clusters, and the vast cosmic web of matter that we observe today. By studying the detailed patterns in the CMB, scientists can learn how these structures formed and evolved over billions of years, from the tiny fluctuations present just 380,000 years after the Big Bang to the massive superclusters and voids we see today. In this way, the CMB not only reveals the universe's past but also allows us to predict its future. The information encoded in the CMB provides critical data for cosmological models, which in turn predict the universe's ultimate fate. Based on current CMB measurements, combined with observations of the large-scale structure of the universe and the behavior of distant supernovae, scientists have concluded that the universe is currently in a phase of accelerated expansion, driven by the mysterious force known as dark energy. If this expansion continues indefinitely, the universe will eventually experience a big freeze, where galaxies, stars, and planets drift farther apart, the stars burn out, and the universe becomes a cold, dark, and empty place. However, alternative scenarios for the universe's future are still on the table. If dark energy behaves differently than we currently expect, it could cause the universe to stop expanding and collapse in on itself, leading to a big crunch. Or, in an even more extreme scenario, dark energy could increase in strength over time, eventually ripping apart galaxies, stars, planets, and even atoms in a big rip. The CMB, while providing invaluable information about the universe's past and present, also holds the potential to refine our understanding of dark energy and, in turn, help us predict the ultimate fate of the cosmos. As our instruments become more advanced and our understanding of physics deepens, the CMB will continue to play a central role in cosmology. New missions, such as the upcoming CMB-S4 experiment, are set to provide even more precise measurements of the CMB, probing deeper into the mysteries of the universe. These experiments will allow us to test competing models of inflation, explore the nature of dark energy and dark matter, and possibly even detect the faint signature of primordial gravitational waves. Each new piece of data brings us closer to answering some of the most profound questions about the universe, but it also raises new ones, ensuring that the study of the CMB will remain a vibrant and exciting field of research for years to come. As we look up at the night sky, we are reminded that the universe is far more ancient and mysterious than we could have ever imagined. The CMB, the faint afterglow of the Big Bang, is a testament to the power of human curiosity and ingenuity. Through the careful study of this relic radiation, we have uncovered the history of the cosmos, from its fiery birth to its current state of accelerated expansion. And yet, as much as we have learned, the CMB continues to challenge us, offering tantalizing clues to the universe's deepest secrets. Whether it's the search for primordial gravitational waves, the mystery of dark energy, or the possibility of other universes beyond our own, the CMB stands as a reminder that the universe still holds many mysteries waiting to be uncovered. The Cosmic Microwave Background (CMB) serves as both a time capsule and a beacon for cosmologists, allowing them to peer back in time to the birth of the universe while also guiding them toward the unexplored frontiers of physics. As much as the CMB has illuminated our understanding of the cosmos, it has also raised profound questions that continue to challenge our most fundamental theories. One of the biggest puzzles tied to the CMB is its connection to dark matter. Dark matter is an enigmatic substance that neither emits nor absorbs light, making it invisible and detectable only through its gravitational effects. Despite being elusive, dark matter is thought to make up about 27% of the universe's total mass energy content, vastly outstripping ordinary matter, which comprises just 5%. The CMB provides critical insights into the nature and distribution of dark matter, even though it remains hidden from direct observation. The temperature fluctuations observed in the CMB tell us that dark matter must have played a significant role in the formation of the universe's large-scale structure. In the early universe, regions with slightly higher than average densities of dark matter acted as gravitational wells, pulling in surrounding matter and eventually leading to the formation of galaxies, stars, and clusters of galaxies. Without dark matter, the ordinary matter alone would not have been able to coalesce quickly enough to form these structures in the 13.8 billion years since the Big Bang. Interestingly, the CMB's precise measurements have allowed cosmologists to infer the amount and distribution of dark matter in the early universe. This, in turn, has helped to constrain various models of dark matter, ruling out certain candidates while favoring others. For instance, one of the leading candidates for dark matter is a class of particles known as WIMPs, weakly interacting massive particles. If WIMPs exist, their presence would have left a distinct signature in the CMB, as their gravitational effects would influence the pattern of temperature fluctuations. So far, CMB data seems to support the existence of cold dark matter, meaning that dark matter is made up of slow-moving particles that interact only weakly with other matter and radiation. However, the exact nature of dark matter remains one of the biggest open questions in cosmology, and future CMB experiments could provide the key to solving this mystery. While the CMB has revealed much about dark matter, it has also led to some surprising insights about dark energy, another mysterious force that permeates the universe. Dark energy, which accounts for approximately 68% of the universe's energy density, is believed to be responsible for the accelerated expansion of the universe. The discovery of this accelerated expansion in the late 1990s was one of the most shocking findings in modern cosmology, and it has forced scientists to rethink their understanding of the universe's fate. The CMB plays a crucial role in studying dark energy because the patterns of temperature and polarization fluctuations in the CMB depend on how the universe has expanded over time. By comparing the observed CMB patterns to predictions from various cosmological models, scientists can infer how much dark energy there is and how it has influenced the universe's expansion. Current CMB data, combined with other observations, suggests that dark energy has remained relatively constant over time, consistent with the simplest model of dark energy known as the cosmological constant. However, there are other possible models of dark energy, some of which predict that its properties could change over time, leading to different scenarios for the universe's future. One of the most tantalizing possibilities is that dark energy could eventually decay or transition into another form of energy, dramatically altering the fate of the universe. If dark energy were to decay, the expansion of the universe could slow down or even reverse, leading to a future where the universe collapses in a big crunch. Alternatively, if dark energy were to increase in strength, it could lead to the aforementioned Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. While current CMB data favors the cosmological constant model, future observations could help to distinguish between these scenarios and provide a clearer picture of the universe's ultimate fate. Beyond dark matter and dark energy, the CMB has also sparked debates about the possibility of a multiverse, a collection of multiple, possibly infinite, universes that exist alongside our own. One of the key predictions of inflationary theory is that inflation did not just happen once but may have occurred in different regions of space at different times, creating multiple, bubble, universes with varying physical laws. According to this idea, our universe is just one bubble in a much larger multiverse, and the CMB could hold clues to the existence of these other universes. In theory, if our universe interacted with another universe early in its history, this interaction could leave an imprint on the CMB in the form of unusual temperature fluctuations or patterns that cannot be explained by standard cosmological models. Some researchers have speculated that certain anomalies in the CMB, such as the cold spot and the axis of evil, could be evidence of such an interaction. However, these claims remain highly speculative, and more data is needed to determine whether these anomalies are truly the result of a multiverse or simply statistical flukes. Despite the tantalizing possibility of a multiverse, there is currently no direct evidence for the existence of other universes, and the idea remains one of the most controversial topics in cosmology. However, the continued study of the CMB, along with advancements in observational technology, could one day provide the data needed to either confirm or rule out this mind-bending hypothesis. The CMB's contribution to our understanding of cosmology does not end with dark matter, dark energy, or the multiverse. One of the most exciting frontiers in CMB research is the search for primordial gravitational waves. These ripples in spacetime were predicted by Einstein's theory of general relativity and are thought to have been produced during inflation. If they exist, primordial gravitational waves would leave a distinctive imprint on the polarization of the CMB, creating a unique pattern known as B-mode polarization. Detecting B-mode polarization would provide direct evidence for inflation and could even reveal the energy scale at which inflation occurred. This would be a groundbreaking discovery, as it would allow scientists to probe physics at energies far higher than anything achievable in particle accelerators, shedding light on the unification of the fundamental forces and the nature of quantum gravity. Several experiments, including the BICEP-2 experiment in Antarctica, have attempted to detect B-mode polarization in the CMB. In 2014, BICEP-2 made headlines when it announced the possible detection of B-modes, which was initially hailed as evidence for primordial gravitational waves and inflation. However, further analysis revealed that the signal was likely caused by dust in our own galaxy rather than by primordial gravitational waves. Despite this setback, the search for B-mode polarization continues, and future experiments, such as CMBS-4, are expected to provide more sensitive measurements that could finally confirm the existence of these elusive gravitational waves. The potential discovery of primordial gravitational waves would be a major milestone in our quest to understand the universe's origins and the fundamental laws of nature. It would provide a direct link between the CMB, inflation, and quantum gravity, opening up new avenues of research into the deepest mysteries of the cosmos. The cosmic microwave background remains one of the most important and mysterious phenomena in cosmology. It has provided us with a window into the early universe, allowing us to test our theories of cosmic evolution and to explore some of the most profound questions about the universe's origin, structure, and fate. From the flatness of the universe to the nature of dark matter and dark energy, from the possibility of a multiverse to the search for primordial gravitational waves, the CMB continues to challenge and inspire scientists as they seek to unravel the mysteries of the cosmos. As we look to the future, new experiments and observations will undoubtedly deepen our understanding of the CMB and its implications for the universe. Whether we discover evidence for new physics, confirm the existence of a multiverse, or detect the telltale signs of inflation, the study of the CMB will remain at the forefront of cosmology, guiding us toward new discoveries and helping us to better understand our place in the vast and mysterious universe. The study of the cosmic microwave background (CMB) has brought us astonishingly far in understanding the history and structure of the universe, but it has also left us with a host of perplexing questions. Among these are deeper inquiries into the true nature of the early universe, the formation of cosmic structures, and the forces driving the universe's expansion. By continuously refining our observations of the CMB, scientists are hoping to push the boundaries of what we know and delve further into the fundamental aspects of cosmology. A particularly intriguing aspect of the CMB is its role in addressing one of the most important unresolved questions in cosmology: the issue of cosmic inflation. Inflation, the brief period of exponential expansion that occurred just after the Big Bang, is the leading theory to explain why the universe appears so uniform and isotropic on large scales. Without inflation, it would be difficult to explain why distant regions of the universe, which should have had no opportunity to exchange information or energy, exhibit nearly identical temperatures and properties. The concept of inflation, proposed by physicist Alan Guth in 1980, suggests that the universe underwent a period of extremely rapid expansion during the first fraction of a second after the Big Bang. This inflationary phase would have stretched out any initial irregularities, smoothing the universe and leaving behind only tiny fluctuations in the density of matter. These fluctuations would later grow into the galaxies, clusters, and other large-scale structures that we observe today. One of the major triumphs of inflationary theory is that it predicts the exact form of the fluctuations observed in the CMB. The temperature variations seen in the CMB are thought to be the result of quantum fluctuations that were amplified during inflation, creating regions of slightly higher or lower density. These regions eventually evolved into the cosmic structures that fill the universe today. The fact that inflation correctly predicts the statistical properties of the CMB is one of the strongest pieces of evidence in favor of the theory. However, while inflation is widely accepted, it is not without its challenges. For one, there are many different models of inflation, each predicting slightly different outcomes for the early universe. Determining which model is correct, or if inflation happened at all, requires more precise measurements of the CMB, particularly its polarization. As mentioned earlier, the detection of B-mode polarization would provide a smoking gun for inflation, offering direct evidence of the gravitational waves produced during this rapid expansion. Another major question that the CMB might help answer is related to the so-called curvature of the universe. One of the remarkable features of the universe, as revealed by CMB data, is that it appears to be flat, meaning that parallel lines never converge or diverge. This flatness is somewhat surprising, given that a slightly curved universe, either positively curved like a sphere or negatively curved like a saddle, would seem to be more natural given the dynamics of cosmic expansion. Inflation offers a solution to this puzzle by suggesting that the rapid expansion of space would have flattened any initial curvature, much like how a small portion of the surface of a balloon appears flat when the balloon is inflated. While current CMB data indicates that the universe is very close to flat, small deviations from perfect flatness could still exist, and future experiments may be able to detect these subtle deviations. Such a discovery would have profound implications for our understanding of the universe's geometry and the physics of the early universe. Yet another puzzle that the CMB may help to unravel is the mystery of the universe's isotropy, its apparent uniformity in all directions. While the CMB is remarkably smooth, there are some curious anomalies that challenge the idea of perfect isotropy. For example, the CMB contains a cold spot, an unusually large region that is slightly cooler than the surrounding areas. This cold spot has been the subject of much debate, with some researchers suggesting that it could be the result of a massive supervoid, a vast, underdense region of space, while others have speculated that it could be evidence of more exotic phenomena, such as the interaction with another universe in the multiverse. Additionally, there is the so-called axis of evil, a peculiar alignment of temperature fluctuations in the CMB that seems to suggest that the universe has a preferred direction, which contradicts the standard cosmological principle of isotropy. While these anomalies could be the result of random statistical fluctuations, they continue to provoke interest and raise questions about whether there may be unknown physical processes at play in the early universe. One of the most exciting prospects for future CMB research is the possibility of using the CMB to explore new physics beyond the Standard Model. The Standard Model of particle physics, which describes the behavior of fundamental particles and forces, has been extraordinarily successful in explaining a wide range of phenomena. However, it is incomplete, as it does not account for gravity, dark matter, dark energy, or the unification of the fundamental forces at high energies. By studying the CMB with greater precision, scientists hope to uncover hints of new physics that could extend or modify the Standard Model. For example, the CMB could provide evidence for the existence of additional particles or forces that only existed in the early universe. These particles, known as relics, would have influenced the evolution of the universe and left an imprint on the CMB. Discovering such relics would open up new avenues of research into the fundamental nature of matter and energy. The CMB could also provide clues about the nature of quantum gravity, the as yet unresolved theory that seeks to unify quantum mechanics and general relativity. Inflationary models, for instance, are intimately connected to quantum gravity, as they involve physics at energy scales where both quantum effects and gravitational effects are significant. By studying the CMB, scientists may be able to gain insights into how gravity behaves at these extreme energies, shedding light on one of the biggest open questions in modern physics. Moreover, the CMB may help to resolve the so-called cosmological constant problem, which arises from the fact that the observed value of dark energy is vastly smaller than the value predicted by quantum field theory. This discrepancy, known as the vacuum catastrophe, is one of the greatest unsolved problems in theoretical physics. The CMB provides a direct window into the history of dark energy and its effects on the expansion of the universe, and future observations could help to clarify the nature of this mysterious force. In addition to providing answers to these deep cosmological questions, the CMB also holds practical applications for understanding the formation and evolution of galaxies and other cosmic structures. The temperature fluctuations in the CMB, known as anisotropies, provide a blueprint for how matter was distributed in the early universe. By studying these anisotropies in greater detail, scientists can gain insights into how galaxies, stars, and clusters formed and evolved over time. One of the key challenges in this area of research is understanding the role of baryon acoustic oscillations, BAOs, which are the ripples in the distribution of matter caused by sound waves in the early universe. These oscillations are visible in the CMB as regular patterns in the temperature fluctuations, and they have also been observed in the large-scale structure of galaxies. By comparing the CMB with observations of BAOs in galaxies, scientists can map the expansion history of the universe and test theories of cosmic evolution. The CMB also plays a vital role in understanding the reionization era, a period that occurred several 100 million years after the Big Bang when the first stars and galaxies formed and began to ionize the surrounding gas. This epoch is crucial for understanding the transition from the relatively simple universe of the CMB to the complex universe of galaxies and other structures that we see today. By studying the CMB's polarization, scientists can learn more about the timing and nature of reionization, which has important implications for galaxy formation and the evolution of the universe. As we continue to explore the mysteries of the CMB, new technological advancements are allowing scientists to observe the universe in even greater detail. Upcoming CMB experiments, such as the Simons Observatory and the CMB-S4 project, aim to improve the precision of CMB measurements by orders of magnitude, providing unprecedented insights into the early universe and the fundamental forces that govern it. These experiments will be able to detect even fainter temperature and polarization signals, allowing researchers to test theories of inflation, dark matter, and dark energy with greater accuracy. The quest to understand the cosmic microwave background is far from over, and future discoveries will undoubtedly reshape our understanding of the universe. With each new observation, the CMB continues to reveal hidden aspects of the cosmos, offering a glimpse into the universe's origins and its ultimate fate. As scientists continue to unravel the secrets of the CMB, they are not only probing the history of the universe but also laying the groundwork for new and revolutionary theories that will expand our knowledge of physics and cosmology. The study of the CMB represents one of the most profound scientific endeavors ever undertaken. It is a testament to humanity's ability to look beyond the confines of our planet and into the vast, mysterious universe that surrounds us. Through the cosmic microwave background, we are able to witness the birth of the universe and glimpse the physical processes that shaped everything we see today. It is a reminder of how far we have come in our understanding of the cosmos, and how much further we still have to go. As we continue to unravel the mysteries hidden within the cosmic microwave background CMB, it's clear that this faint glow from the early universe holds the key to understanding not only how the universe began but also how it will evolve in the future. The CMB acts as a kind of cosmic fossil, offering scientists a wealth of information about the universe when it was just a few 100,000 years old. The knowledge gleaned from studying the CMB has implications not only for cosmology but also for fields such as particle physics, quantum mechanics, and even philosophy, as it challenges and reshapes our fundamental understanding of reality. One of the major revelations provided by the CMB is the confirmation of the universe's homogeneity and isotropy on large scales. Homogeneity means that the universe is essentially the same in every direction, with no preferred points or regions. Isotropy, on the other hand, refers to the idea that the universe looks the same regardless of the direction we observe. These two principles form the foundation of what is known as the cosmological principle, which assumes that the universe is both homogeneous and isotropic on the largest scales. The discovery of the CMB provided the first observational evidence supporting this principle, as it shows that the universe was incredibly uniform shortly after the Big Bang, with only tiny fluctuations in temperature and density. These small fluctuations, as mentioned earlier, represent the seeds of the cosmic structures we see today: galaxies, clusters, and superclusters. The fact that the universe appears so uniform over vast distances remains one of the great mysteries in cosmology, and it is directly tied to the theory of cosmic inflation, which attempts to explain how such uniformity could arise in a universe that began in such a chaotic and energetic state. The implications of the CMB's uniformity extend beyond cosmology. They also challenge our understanding of the fundamental forces and particles that govern the universe. The early universe, as revealed by the CMB, was a hot, dense plasma consisting of protons, neutrons, electrons, and photons, all interacting in a kind of cosmic soup. As the universe expanded and cooled, these particles began to decouple, allowing light to travel freely for the first time. This moment of recombination, when electrons combined with protons to form neutral hydrogen atoms, is what gave rise to the CMB. The behavior of these particles and their interactions during the early universe is governed by the Standard Model of Particle Physics, which describes the electromagnetic, weak, and strong nuclear forces. However, the extreme conditions of the early universe also suggest that there may be forces or particles that have not yet been discovered, particularly at the high energies associated with the moments immediately following the Big Bang. The CMB, therefore, offers a unique opportunity to test the limits of the Standard Model and to search for signs of new physics that could help explain the behavior of matter and energy at these early times. One of the most exciting areas of research in this regard is the search for dark matter and dark energy, two mysterious substances that are believed to make up most of the universe's mass and energy content but have yet to be directly observed. The existence of dark matter was first proposed to explain the gravitational effects observed in galaxies and clusters, which could not be accounted for by the visible matter alone. Dark energy, on the other hand, was introduced to explain the observed acceleration in the universe's expansion, a discovery that earned the Nobel Prize in Physics in 2011. The CMB provides crucial evidence for both dark matter and dark energy. The pattern of temperature fluctuations in the CMB suggests that the universe is composed of roughly 5% ordinary matter, 25% dark matter, and 70% dark energy. This distribution is essential for explaining the observed structure of the universe, as dark matter provides the gravitational scaffolding around which galaxies and clusters formed, while dark energy drives the universe's accelerated expansion. Understanding the exact nature of dark matter and dark energy remains one of the biggest challenges in modern physics, and the CMB continues to offer important clues in this quest. In addition to dark matter and dark energy, the CMB has also played a key role in refining our understanding of the universe's age and size. By analyzing the temperature fluctuations in the CMB, scientists have been able to determine the age of the universe with remarkable precision, estimating it to be around 13.8 billion years old. This is a significant achievement, as it provides a clear timeline for the evolution of the universe, from the Big Bang to the present day. The size of the observable universe, meanwhile, is determined by the horizon of the CMB, the distance that light has been able to travel since the universe became transparent. This horizon defines the limits of what we can observe, as any region beyond it has not had enough time to send light or other signals to us. The size of the observable universe is currently estimated to be about 93 billion light-years in diameter, though the universe itself may be much larger, or even infinite, beyond this observable horizon. As the study of the CMB has progressed, researchers have continued to develop new techniques and technologies to extract even more detailed information from this ancient light. The development of advanced telescopes, such as the Planck satellite and the Atacama Cosmology Telescope, has allowed scientists to measure the CMB with greater precision than ever before, revealing finer details in the temperature fluctuations and polarization patterns. One of the key areas of focus for future research is the search for primordial gravitational waves, which are ripples in spacetime that would have been generated during the inflationary period of the early universe. These gravitational waves would leave a subtle imprint on the polarization of the CMB, creating the characteristic B-mode pattern mentioned earlier. Detecting these primordial gravitational waves would provide direct evidence for inflation and offer a glimpse into the physics of the very earliest moments of the universe. The detection of B-mode polarization is an incredibly challenging task, as the signal is extremely faint and must be distinguished from other sources of noise, such as the gravitational lensing caused by intervening matter and the foreground emissions from our galaxy. However, if successful, this discovery would revolutionize our understanding of the early universe and provide a direct link between cosmology and quantum gravity. In addition to gravitational waves, future CMB research is also focused on understanding the so-called reionization period of the universe. Reionization occurred several 100 million years after the Big Bang, when the first stars and galaxies began to form and ionize the surrounding hydrogen gas. This process left a distinct signature on the CMB's polarization, which scientists are now trying to measure with greater accuracy. Understanding the timing and nature of reionization is crucial for understanding how the first structures in the universe formed and how they evolved over time. As technology continues to advance, new experiments and missions are being planned to probe the CMB with even greater sensitivity. One of the most ambitious of these is the proposed CMB-S4 project, which aims to create a network of ground-based telescopes capable of measuring the CMB's polarization with unprecedented precision. This project, along with other future missions, promises to push the boundaries of what we know about the universe and unlock new discoveries about its earliest moments and ultimate fate. But even as we continue to gather more data and refine our theories, the study of the CMB reminds us that there are still deep mysteries waiting to be solved. The nature of dark matter and dark energy, the origin of inflation, the possibility of multiple universes, and the search for new particles and forces, all of these questions remain at the forefront of cosmological research. The CMB provides a window into the past, but it also opens up new possibilities for the future, offering tantalizing hints about the unknown aspects of the universe. As we look ahead to the future of CMB research, one thing is clear: the study of the cosmic microwave background has fundamentally transformed our understanding of the universe and our place within it. From its discovery in the 1960s to the present day, the CMB has been a cornerstone of modern cosmology, providing critical evidence for the Big Bang, inflation, dark matter, and dark energy. It has revealed the universe's structure, age, and composition, and has opened up new avenues of research into the most profound questions in physics and cosmology. In many ways, the CMB is a cosmic time capsule, preserving the light from the universe's earliest moments, and carrying it across billions of years of space and time. By studying this light, we are not only uncovering the history of the universe but also unlocking the secrets of the fundamental laws that govern it. The CMB is a testament to the power of human curiosity and the ability of science to push the boundaries of knowledge, revealing the hidden complexities of the cosmos and offering new insights into the nature of reality itself. As we continue to explore the CMB and its implications, we are reminded of just how much we still have to learn about the universe. Every new discovery raises new questions, and the journey to understand the cosmos is far from over. The study of the CMB is a never-ending quest, one that will continue to shape the future of cosmology and deepen our understanding of the universe for generations to come. The ongoing study of the cosmic microwave background (CMB) continues to serve as one of the most profound endeavors in modern science, pushing the boundaries of human understanding of the universe. With each new discovery, we are presented with an even greater set of questions, pointing toward both the mysteries of the early universe and the unseen forces that govern its evolution. As we dive deeper into the CMB's intricate details, the depth and scope of its implications seem limitless, spanning from the birth of the cosmos to its eventual fate. The cosmic microwave background not only tells us about the early universe but also serves as a tool for testing our theories of cosmology. One example of this is the ongoing debate surrounding the Hubble tension. The Hubble constant is a key value that describes the rate of the universe's expansion. Measurements of this constant using the CMB suggest one value, while measurements based on the behavior of more local galaxies suggest a slightly higher value. This discrepancy, known as the Hubble tension, has become one of the biggest puzzles in modern cosmology. The CMB-derived Hubble constant relies on our understanding of the early universe and the physical processes that governed it. Local measurements of the Hubble constant, on the other hand, rely on observing distant objects like supernovae and galaxies and estimating their distances and velocities. The fact that these two methods produce different results has led scientists to speculate that something fundamental may be missing from our current models of the universe. Some researchers have suggested that this discrepancy could point to new physics beyond the standard model, such as the existence of additional forms of dark energy, or even new particles that were present in the early universe but have since decayed or disappeared. Others argue that it may be related to how we understand the behavior of dark matter or other unknown components of the universe. In either case, the CMB continues to provide critical data that helps refine these models and pushes the boundaries of what we know about the cosmos. In addition to the Hubble tension, the study of the CMB has also led to important insights into the geometry and fate of the universe. One of the most fundamental questions in cosmology is whether the universe is flat, open, or closed, meaning whether it will continue expanding forever, eventually collapse in on itself, or reach some kind of equilibrium. The CMB offers important clues to this question by revealing the curvature of spacetime on large scales. By analyzing the pattern of temperature fluctuations in the CMB, scientists have determined that the universe is remarkably flat, meaning that its overall geometry is not curved like a sphere or saddle. This finding has significant implications for the future of the universe, as a flat universe suggests that it will continue expanding indefinitely. However, the rate of this expansion depends on the amount of dark energy present in the universe, as dark energy is responsible for driving the acceleration of cosmic expansion. The discovery that the universe's expansion is accelerating, first made in the late 1990s, was one of the most groundbreaking revelations in modern astronomy. It suggested that the universe is not just expanding but doing so at an increasing rate, driven by a mysterious form of energy that permeates all of space. The CMB provides a critical piece of evidence for this acceleration, as its patterns of temperature and polarization help scientists model the effects of dark energy on the universe's evolution. Understanding the exact nature of dark energy remains one of the greatest challenges in cosmology. While we know that it makes up about 70% of the universe's total energy content, its origin and properties are still largely unknown. Some theories suggest that dark energy could be related to the cosmological constant, a term first introduced by Albert Einstein to describe a repulsive force that counteracts gravity on large scales. Others propose that dark energy could be the result of new physical fields or forces that have yet to be discovered. The CMB, with its unparalleled ability to probe the early universe, offers a unique opportunity to test these theories. By measuring the way dark energy has affected the growth of cosmic structures over time, scientists can gain insight into its properties and its role in the universe's future. One possibility is that dark energy is not constant but changes over time, potentially leading to different scenarios for the ultimate fate of the cosmos. One such scenario is the Big Freeze, in which the universe continues expanding forever, gradually cooling and becoming more diffuse as galaxies move farther apart and stars burn out. Another possibility is the Big Rip, in which dark energy becomes so powerful that it eventually tears apart galaxies, stars, and even atoms. A third scenario is the Big Crunch, in which the universe's expansion eventually reverses, causing it to collapse in on itself. The CMB, with its detailed record of the universe's past, provides essential data that helps scientists evaluate these possibilities and predict what might happen billions of years into the future. In addition to its role in studying dark energy, the CMB has also opened up new avenues of research in quantum mechanics and the nature of spacetime itself. The early universe, as revealed by the CMB, was a highly energetic environment where quantum effects played a significant role in shaping the universe's structure. The tiny fluctuations in the CMB are believed to be the result of quantum fluctuations during inflation, meaning that the seeds of cosmic structures were laid down by quantum processes. This connection between quantum mechanics and cosmology is one of the most exciting frontiers of modern physics. It suggests that the universe on the largest scales is governed by the same principles that operate on the smallest scales, linking the behavior of galaxies and stars to the bizarre and counterintuitive world of quantum particles. The CMB offers a unique opportunity to study these processes in action, providing a bridge between the macroscopic and microscopic realms of the universe. One of the most intriguing possibilities raised by this connection is the idea of a multiverse. The idea that our universe may be just one of many universes that exist within a larger multiverse. Some theories of cosmic inflation suggest that inflation may not have stopped everywhere at the same time, leading to the creation of pocket universes with different physical laws and properties. The CMB could provide evidence for the existence of such a multiverse, as it may contain subtle imprints of collisions or interactions with other universes. The search for evidence of the multiverse is still in its early stages, but the CMB remains one of the most promising tools for exploring this possibility. By analyzing the fine details of the CMB's temperature and polarization patterns, scientists hope to find signs of anomalies or irregularities that could point to the existence of other universes. While no definitive evidence has been found so far, the study of the CMB continues to push the boundaries of our understanding of the universe and its place within the broader cosmos. As we look to the future, the study of the CMB promises to remain a central focus of cosmological research. New experiments and missions, such as the proposed CMB-S4 project and future space-based observatories, will provide even more detailed measurements of the CMB's temperature, polarization, and gravitational effects. These observations will help scientists refine their models of the early universe, test new theories of physics, and explore the deepest mysteries of the cosmos. The CMB is not just a relic of the past, it is a living record of the universe's history, carrying with it the imprints of the forces and processes that shape the cosmos from its earliest moments to the present day. By studying this ancient light, we are not only uncovering the secrets of the universe's birth but also opening up new possibilities for understanding its future and the fundamental laws that govern it. The CMB serves as a reminder of the power of human curiosity and the incredible potential of science to reveal the hidden complexities of the universe. As we continue to explore the CMB and its many mysteries, we are reminded of how much we still have to learn. Every new discovery raises new questions, and the journey to understand the cosmos is far from over. The study of the CMB is a never-ending quest, one that will continue to shape the future of cosmology and deepen our understanding of the universe for generations to come. The Cosmic Microwave Background (CMB) holds a special place in our understanding of the universe's evolution, and its study will likely remain at the forefront of cosmology for many years. As technology and observational techniques improve, researchers are confident that the CMB will continue to yield more detailed insights about both the early and present universe. To fully appreciate the gravity of what the CMB reveals, it's important to recognize that this ancient radiation contains crucial information not just about cosmic expansion and the large-scale structure of the universe, but also about more enigmatic phenomena, such as dark matter and dark energy. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible to traditional telescopes. However, it exerts gravitational effects that can be detected, such as its role in holding galaxies together. The CMB offers indirect clues about the nature of dark matter because its presence influenced the formation of structures in the universe. Scientists can infer the distribution of dark matter by examining how the CMB's tiny temperature fluctuations contributed to the clustering of galaxies and other cosmic structures. As the universe cooled after the Big Bang, atoms formed, allowing photons, light particles, to travel freely and create the CMB. Before this moment, the universe was too hot and dense for light to travel unimpeded. The temperature fluctuations in the CMB are thus a fossil record of this early time, showing how the clumping of matter, both normal and dark, was already shaping the universe's large-scale structure. By carefully analyzing these fluctuations, cosmologists have been able to map the density variations that eventually gave rise to galaxies, clusters, and voids. However, dark matter itself remains a profound mystery. Despite its gravitational influence, scientists have yet to identify what dark matter is made of. Leading candidates include weakly interacting massive particles, WIMPs, sterile neutrinos, or even primordial black holes. The CMB could help narrow down these possibilities by providing data on how dark matter interacted with regular matter and radiation during the early universe. Specifically, the precise measurements of the CMB's temperature and polarization offer a way to test different models of dark matter, as each model predicts slightly different effects on the CMB's structure. Even more mysterious than dark matter is dark energy, which makes up about 70% of the universe and is thought to be responsible for the accelerating expansion of the cosmos. Dark energy was only discovered in the late 1990s through observations of distant supernovae, but its effects can also be seen in the CMB. The CMB provides a snapshot of the universe when it was just 380,000 years old, and by comparing this snapshot with the current state of the universe, scientists can measure how dark energy has influenced cosmic expansion over time. One of the most intriguing possibilities is that dark energy might not be constant but could change over time. This raises the question of whether dark energy could eventually lead to radically different outcomes for the universe's future. As mentioned earlier, one possibility is the Big Rip, in which dark energy grows stronger over time, eventually tearing apart galaxies, stars, and even atoms. Another possibility is that dark energy might decay or change form, leading to a slower expansion or even a Big Crunch, where the universe collapses back in on itself. The study of the CMB has also opened up new avenues for investigating the fundamental nature of spacetime itself. One of the most exciting areas of research involves the search for primordial gravitational waves, ripples in spacetime that were generated during the universe's inflationary period. These waves would have left a faint imprint on the polarization of the CMB, and detecting them would provide direct evidence for inflation and offer insights into the quantum nature of gravity. In 2014, the BICEP-2 experiment made headlines when it claimed to have detected evidence of primordial gravitational waves in the CMB's polarization. However, further analysis showed that the signal was likely caused by interstellar dust rather than primordial gravitational waves. Despite this setback, the search for these elusive waves continues, with new experiments such as the Simons Observatory and the proposed CMB-S4 project aiming to make even more sensitive measurements of the CMB's polarization. If primordial gravitational waves are detected, it would be a groundbreaking discovery, providing a window into the universe's earliest moments and offering clues about how quantum fluctuations in the fabric of spacetime gave rise to the universe as we know it. It would also open up new possibilities for unifying general relativity, which describes gravity on large scales, with quantum mechanics, which governs the behavior of particles on the smallest scales. The study of the CMB has also raised intriguing questions about the possibility of new physics beyond the standard model. For example, some researchers have suggested that the universe might have additional forms of matter or energy that we have yet to discover. One possibility is that there could be additional particles, such as sterile neutrinos, which interact only with gravity and not with the other forces of nature. The CMB provides a way to test these theories by looking for deviations from the standard predictions of how matter and energy should behave in the early universe. Another possibility is that the laws of physics themselves might vary across different regions of the universe. The idea of a multiverse, in which different regions of space have different physical properties or even different laws of physics, has been proposed as a way to explain certain fine-tuning problems in cosmology, such as why the constants of nature appear to be perfectly suited for the existence of life. The CMB could provide evidence for the multiverse by revealing subtle anomalies or patterns that suggest interactions with other, pocket, universes. Although the idea of the multiverse remains speculative, it represents one of the most profound possibilities for the future of cosmology. If true, it would mean that our universe is just one of many, each with its own unique properties and histories. The CMB might be our best chance of detecting evidence of these other universes, offering a glimpse into the broader reality that lies beyond our own. As we continue to study the CMB, we are reminded of how much we have yet to learn about the universe. The CMB is not just a relic of the past but a gateway to the future, offering clues about the fundamental nature of reality and the forces that govern the cosmos. Whether it's uncovering the mysteries of dark matter and dark energy, probing the origins of space-time itself, or exploring the possibility of a multiverse, the CMB remains one of the most important and exciting areas of scientific research. The cosmic microwave background is a powerful tool for understanding the universe's origins and its future trajectory. From revealing the universe's flat geometry to shedding light on the mysterious forces of dark matter and dark energy, the CMB provides a wealth of information that continues to challenge and expand our understanding of the cosmos. As we look ahead, new technologies and missions will allow us to delve even deeper into the CMB's secrets, offering the potential for groundbreaking discoveries that could reshape our view of the universe and our place within it. The journey of cosmic exploration, guided by the light of the CMB, is far from over, and each new revelation brings us closer to answering some of the most profound questions ever asked by humanity. The cosmic microwave background (CMB) is truly a treasure trove of cosmic information, and as our technology improves, so too does our ability to extract more nuanced and detailed insights from it. In the decades since its discovery, the CMB has already provided us with a framework for understanding the universe's infancy and allowed us to peer into events that transpired almost 14 billion years ago. However, one of the most compelling aspects of the CMB is that it could be the key to unlocking deeper mysteries that transcend our current knowledge, offering us glimpses into the uncharted realms of cosmology. The CMB is sometimes referred to as the afterglow of creation, a poetic description that belies its profound significance. The light we detect as the CMB was emitted when the universe was only about 380,000 years old, a mere blink in cosmic terms. This period marks the end of what cosmologists call the Dark Ages, a time when the universe was opaque to radiation because free electrons scattered light. As the universe expanded and cooled, these electrons combined with protons to form neutral hydrogen atoms, a process known as recombination. With fewer free electrons to scatter light, photons were suddenly free to travel across space, creating what we now observe as the CMB. But why is the CMB so cold? After all, the universe was extremely hot during its early moments, with temperatures soaring into the billions of degrees. The answer lies in the continuous expansion of the universe. As space expands, it stretches the wavelengths of light, a process known as redshifting. This stretching dilutes the energy of the photons, cooling them over time. By the time the CMB reaches us, the temperature has dropped to just 2.725 K, a temperature only slightly above absolute zero. This cooling effect is one of the many ways the CMB encapsulates the history of the universe's evolution. The CMB is not uniform, though. As mentioned earlier, it contains tiny fluctuations, imperfections in its smoothness that are just a few parts in 100,000. These temperature differences, though minuscule, are critically important because they tell us about the initial conditions that seeded the formation of galaxies and large-scale structures in the universe. It's from these fluctuations that cosmologists have been able to build detailed models of the universe's contents, including ordinary matter, and dark energy. The discovery of the CMB by Arno Penzias and Robert Wilson in 1965 is a fascinating story in its own right. The two radio astronomers were using a microwave antenna at Bell Labs in Holmdel, New Jersey, to conduct experiments unrelated to cosmology. However, they were confounded by a persistent noise that they could not eliminate, no matter where they pointed their instrument. This noise came from every direction in the sky and was the same at all times of day and night. After ruling out possible sources of interference, such as nearby radio stations or even pigeon droppings in the antenna, Penzias and Wilson concluded that they had stumbled upon something extraordinary. At the same time, just a short distance away at Princeton University, a team of theoretical physicists led by Robert Dicke was preparing to search for the very signal that Penzias and Wilson had inadvertently detected. Dick's group had realized that if the Big Bang theory were correct, then the universe should be filled with a faint glow of radiation left over from its hot, dense beginnings. When Penzias and Wilson learned about the Princeton group's work, they quickly understood that their noise was actually the long-sought evidence of the Big Bang. This serendipitous discovery had enormous implications for cosmology, as it provided the most compelling evidence yet that the universe began in a hot, dense state and has been expanding ever since. With the CMB, the Big Bang theory moved from a speculative idea to a well-supported model of cosmic evolution. The discovery earned Penzias and Wilson the Nobel Prize in Physics in 1978 and cemented the CMB's role as one of the most important discoveries in the history of science. But detecting the CMB was just the beginning. In the years that followed, scientists began to map the tiny fluctuations in the CMB's temperature. The first detailed observations came from the Cosmic Background Explorer (COBE) satellite, launched by NASA in 1989. COBE provided the first direct evidence of the small temperature variations that would later be mapped in exquisite detail by subsequent missions like the Wilkinson Microwave Anisotropy Probe (WMAP) and the European Space Agency's Planck satellite. WMAP, launched in 2001, revolutionized our understanding of the universe by providing a full-sky map of the CMB with unprecedented precision. From MAPS data, cosmologists were able to determine key parameters of the universe, including its age, composition, and geometry. One of MAPS' most significant findings was that the universe is flat, meaning that it will continue to expand forever, rather than collapsing in on itself. WMAP also provided strong evidence for the existence of dark energy, the mysterious force driving the accelerated expansion of the universe. The Planck satellite, launched in 2009, took MAPS' work even further by measuring the CMB with even greater sensitivity and resolution. Planck's data has allowed cosmologists to refine their models of the universe's early moments, and has provided new insights into phenomena like cosmic inflation and the distribution of dark matter. Planck's measurements of the CMB's polarization have also opened new avenues for exploring the universe's fundamental properties, including the search for primordial gravitational waves. But despite the incredible success of missions like WMAP and Planck, there is still much we don't understand about the CMB and the universe it reveals. One of the most tantalizing mysteries involves an anomaly in the CMB known as the cold spot. First detected by WMAP and later confirmed by Planck, the cold spot is an unusually large region of the sky where the CMB's temperature is significantly lower than the average. While temperature fluctuations are expected in the CMB, the cold spot is much larger and colder than current models can easily explain. Some researchers have suggested that the cold spot could be the result of a supervoid, a massive region of space with fewer galaxies and less matter than average. A supervoid could cause light from the CMB to lose energy as it passes through, creating the observed cold spot. However, the existence of such a large supervoid has not been confirmed, and other explanations have been proposed, including the possibility that the cold spot could be evidence of exotic physics or even interactions with other universes in a multiverse. The multiverse hypothesis is one of the most speculative but also most exciting ideas in modern cosmology. The basic idea is that our universe might be just one of many, each with its own set of physical laws and constants. If other universes exist, they could have left subtle imprints on the CMB, such as the cold spot or other anomalies. While the multiverse remains a highly controversial and unproven concept, the CMB offers a unique testing ground for these ideas, and future observations may help to shed light on whether our universe is part of a larger cosmic ensemble. The CMB also holds clues about the process of cosmic inflation, the rapid expansion of the universe that occurred in the first fraction of a second after the Big Bang. Inflation is thought to have smoothed out the universe's initial conditions, explaining why the CMB is so uniform across vast distances. However, inflation also predicts the existence of quantum fluctuations that would have been stretched to cosmic scales during the expansion, leaving imprints on the CMB. These fluctuations are what seeded the formation of galaxies and large-scale structures in the universe. One of the key predictions of inflation is the existence of primordial gravitational waves, ripples in space-time produced by the rapid expansion of the early universe. These waves would have left a distinct signature in the polarization of the CMB, and detecting them would provide direct evidence for inflation. As mentioned earlier, the BICEP 2 experiment initially claimed to have found evidence of these waves, but the signal was later attributed to dust in the Milky Way. However, the search for primordial gravitational waves continues, with new experiments underway to make even more sensitive measurements of the CMB's polarization. If primordial gravitational waves are detected, it would be a groundbreaking discovery that could revolutionize our understanding of the universe's origins. It would not only confirm the inflationary model but also offer insights into the quantum nature of gravity, potentially bridging the gap between general relativity and quantum mechanics. Detecting these waves would also provide a window into the universe's earliest moments, allowing us to probe conditions that existed just a tiny fraction of a second after the Big Bang. As the exploration of the cosmic microwave background (CMB) continues, researchers are also delving deeper into the implications of the measurements made by missions like WMAP and Planck. One crucial aspect of the CMB is its power spectrum, a representation of how temperature fluctuations vary with scale across the sky. This power spectrum has become a cornerstone for cosmological analysis and provides a wealth of information about the universe's composition and structure. The power spectrum reveals peaks and troughs that correspond to different scales of temperature fluctuations. The first peak in the spectrum represents the largest scales, which correlate with the sound waves that traveled through the hot plasma of the early universe. These acoustic oscillations were produced by the interplay between gravitational attraction and pressure during the period of recombination. The relative heights of the peaks encode information about the density of ordinary matter, dark matter, and the expansion rate of the universe. In analyzing the CMB power spectrum, cosmologists have discovered that the universe is made up of approximately 68% dark energy, 27% dark matter, and only about 5% ordinary matter. This revelation has led to profound implications for our understanding of cosmic evolution and the fate of the universe. Dark energy, an enigmatic force driving the universe's accelerated expansion, remains one of the biggest puzzles in cosmology, raising questions about the fundamental nature of gravity and the forces shaping our cosmos. The CMB has also provided insights into the geometry of the universe. The measurements indicate that the universe is flat on large scales, a finding that is consistent with inflationary models. A flat universe implies that the total density of matter and energy in the universe is equal to the critical density, which influences how the universe will evolve over time. In a flat universe, space continues to expand forever, but the rate of expansion slows down over time as the gravitational pull of matter eventually balances the expansion. This understanding leads to crucial questions about the ultimate fate of the universe. Will it continue to expand forever, reach a stable state, or eventually collapse in a big crunch? As scientists refine their understanding of the CMB and its implications, they are also keenly aware of the potential for new and unforeseen discoveries. Future observations and experiments will seek to enhance our understanding of the fundamental properties of the universe. The next generation of CMB missions, such as the Simons Observatory and the CMB-S4 project, aim to make even more precise measurements of the CMB, exploring its polarization and improving sensitivity to primordial gravitational waves. These missions hold the promise of probing deeper into the mysteries of the early universe, shedding light on phenomena like inflation and the conditions surrounding the Big Bang. Moreover, the CMB's influence extends beyond cosmology into the realms of particle physics and fundamental physics. Investigating the properties of the CMB can provide insights into beyond standard model physics. For instance, studying the interactions of dark matter with ordinary matter could help elucidate the nature of dark matter itself, one of the most significant unanswered questions in modern astrophysics. This quest could lead to a deeper understanding of the forces and particles that govern the universe at the smallest scales. One avenue of exploration concerns the potential interactions between dark matter and the CMB. If dark matter possesses interactions that affect the distribution of matter in the early universe, this could alter the CMB's temperature fluctuations in measurable ways. Identifying these interactions through CMB observations could reveal the identity of dark matter, whether it consists of weakly interacting massive particles, WIMPs, axions, or another exotic candidate. As our understanding of the CMB deepens, scientists are also grappling with philosophical questions about the nature of reality itself. The CMB represents a bridge between the observable universe and the profound mysteries of existence. It invites us to ponder the fundamental nature of time, space, and the universe's origin. For many cosmologists, the CMB serves as a reminder that our universe is an intricate tapestry woven from the threads of space and time, governed by laws that may still elude our understanding. In the larger context of science, the CMB highlights the interplay between observation and theory. Theoretical frameworks, like the Big Bang model and inflation, guide our expectations, while observational data like the CMB provide the testable evidence that either validates or refines these theories. This dance between theory and observation is one of the defining features of modern science, and reflects humanity's relentless pursuit of knowledge. The CMB's discovery and analysis exemplify how scientific progress is often a collective endeavor, relying on the collaboration of researchers from various disciplines. It showcases how advancements in technology, such as radio astronomy, satellite missions, and computational techniques, can open new frontiers in our understanding of the universe. The story of the CMB is not just about cosmic radiation. It is a narrative of human curiosity, ingenuity, and the quest to understand our place in the cosmos. As we stand at the threshold of further exploration, it is clear that the CMB is far more than a remnant of the Big Bang. It is a powerful tool for deciphering the universe's mysteries. The secrets held within its faint glow will undoubtedly yield more insights into the fabric of reality, the nature of dark energy, and the ultimate fate of the cosmos. The ongoing investigation of the CMB represents a profound chapter in the story of science, one that connects our origins to the vast, intricate universe in which we find ourselves. As we contemplate the significance of the CMB, we can't help but marvel at the cosmic journey it represents, a journey that transcends time and space, inviting us to ponder the very essence of existence. The CMB is a reminder that we are part of a grand narrative, a story written in the language of the cosmos, waiting for us to decode its mysteries and unlock the secrets of the universe. With every observation and analysis of the CMB, we come closer to uncovering the hidden truths of the universe. The CMB not only serves as a relic of the past but also as a beacon for the future, guiding us in our quest to understand the fundamental workings of the cosmos. It invites us to dream big, to explore the uncharted territories of physics and cosmology, and to seek answers to questions that have perplexed humanity for centuries. The legacy of the CMB will endure, inspiring future generations of scientists, dreamers, and explorers. It stands as a testament to our innate desire to understand the world around us and to find our place within the vast and mysterious universe. The journey continues, and as we look to the stars, the CMB will always be there, quietly whispering the secrets of the cosmos to those willing to listen and explore. The cosmic microwave background is not just a remnant of the Big Bang. It is a powerful cosmic tool that enables us to explore the deepest mysteries of the universe. Through the study of the CMB, we gain invaluable insights into the origins, evolution, and ultimate fate of our universe. As we continue to probe the intricacies of the CMB, we are bound to uncover even more profound truths, deepening our understanding of existence itself and expanding the horizons of human knowledge. The exploration of the CMB is a journey without end, a path that promises to unveil the wonders of the universe and inspire future generations to reach for the stars. As we further investigate the cosmic microwave background, CMB, and its implications for our understanding of the universe, it's important to recognize the intricacies involved in studying this faint afterglow of the Big Bang. The CMB is a treasure trove of information, but accessing that information is a complex and delicate endeavor. Scientists employ sophisticated techniques and technology to analyze the CMB, with each observation peeling back another layer of cosmic history. One of the fundamental techniques used in studying the CMB involves mapping its anisotropies, the tiny fluctuations in temperature across the sky. These anisotropies are critical because they reflect the density variations that existed in the early universe. By carefully measuring these temperature differences, cosmologists can infer the distribution of matter and energy shortly after the Big Bang. The mapping process relies on advanced instruments capable of detecting microwave radiation with extraordinary precision. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, was instrumental in creating detailed maps of the CMB. Its findings provided a wealth of data, revealing the temperature fluctuations across the sky and allowing scientists to construct a power spectrum that delineates the characteristics of these fluctuations. MAP's observations confirmed the predictions made by the Big Bang model, helping to solidify our understanding of cosmic evolution. Building on the successes of WMAP, the European Space Agency's Planck satellite was launched in 2009 to enhance our understanding of the CMB further. Planck provided even more detailed measurements of the CMB's anisotropies, significantly improving the precision of cosmological parameters. The data from Planck revealed that the universe is about 13.8 billion years old, a figure that has become a cornerstone of modern cosmology. Planck's observations led to the identification of features in the CMB that hint at the universe's composition, including the density of baryonic matter, and dark energy. One of the most intriguing aspects of Planck's findings is the so-called Hubble tension. This discrepancy arises from the differing values of the Hubble constant, an important measure of the universe's expansion rate, obtained through different methods. While the Planck data suggests a lower value based on the CMB, measurements from other methods, like those using supernovae, yield a higher value. This tension raises questions about the accuracy of our understanding of cosmic expansion and the potential need for new physics beyond the standard cosmological model. Additionally, the study of the CMB has implications for our understanding of inflation, a rapid expansion of the universe that occurred just after the Big Bang. Inflationary theory posits that the universe underwent a brief period of exponential growth, smoothing out irregularities and explaining the uniformity of the CMB. By examining the patterns in the CMB, scientists can test inflationary models and gain insight into the conditions that existed in the earliest moments of the universe. Recent research has even proposed various models of inflation, each with different predictions about the CMB's characteristics. For instance, certain models predict specific patterns of gravitational waves that could be detectable in the polarization of the CMB. Detecting these gravitational waves would not only provide evidence for inflation but also open up a new realm of understanding regarding the nature of space-time and the fundamental forces of the universe. In addition to probing the early universe, the CMB also offers insights into the structure of the cosmos on larger scales. The anisotropies measured in the CMB are closely linked to the large-scale structure of the universe, including galaxies and clusters of galaxies. The distribution of these structures today can be traced back to the tiny fluctuations in density observed in the CMB. By studying these connections, scientists can understand how the universe evolved from a hot, dense state to the vast, complex cosmos we observe today. Furthermore, the CMB can shed light on cosmic events beyond the initial moments of the universe. For example, scientists have been exploring the potential impact of cosmic strings, hypothetical one-dimensional topological defects that may have formed during phase transitions in the early universe. If cosmic strings exist, they could leave detectable imprints in the CMB, providing a new avenue for investigating the universe's evolution. As our observational capabilities improve, researchers are also examining the polarization of the CMB. Polarization refers to the orientation of the light waves and provides additional information beyond temperature measurements. The CMB is polarized due to the scattering of photons off electrons during the period of recombination. By analyzing this polarization, scientists can gain insights into the processes that occurred in the early universe and investigate the nature of dark matter and dark energy. The field of CMB research is rapidly evolving, with new technologies and analytical techniques continually enhancing our understanding. Upcoming experiments aim to push the boundaries of precision and sensitivity further. The next generation of CMB experiments, such as the Simons Observatory and CMB-S4, promises to provide unprecedented insights into the universe's most profound mysteries. These experiments will delve deeper into the polarization of the CMB, explore the intricacies of cosmic inflation, and search for signatures of primordial gravitational waves that could unlock even more secrets about the universe's origins. As scientists continue to analyze the CMB, they are also aware of the potential for unexpected discoveries. The universe often surprises us, and as we probe deeper into its mysteries, we may uncover phenomena that challenge our existing paradigms. This spirit of inquiry drives the quest to understand the cosmos, reminding us that the journey of discovery is as vital as the findings themselves. Beyond the technical aspects, the study of the CMB raises philosophical questions about our place in the universe. The quest to understand the origins of the universe and its subsequent evolution invites contemplation about existence itself. As we seek to comprehend the fabric of reality, we are confronted with profound questions about time, space, and the interconnectedness of all things. The CMB, as a relic of the Big Bang, serves as a reminder of our shared cosmic heritage, a connection that transcends time and invites us to explore the fundamental nature of the universe. The cosmic microwave background is a cornerstone of modern cosmology and a window into the universe's earliest moments. Its discovery and analysis have transformed our understanding of cosmic history, unveiling the mysteries of the Big Bang and the fundamental forces shaping our reality. The ongoing exploration of the CMB promises to yield even more profound insights, deepening our understanding of the cosmos and our place within it. As we continue to investigate this remarkable remnant of the universe's infancy, we are reminded that the journey of discovery is ongoing, a testament to human curiosity and our desire to comprehend the vast and intricate tapestry of existence. The journey into the mysteries of the universe is one of the most exhilarating pursuits humanity can undertake. Through the lens of the cosmic microwave background, we catch a glimpse of the universe's story, a narrative written in the language of cosmic radiation. As we unlock the secrets of the CMB, we not only illuminate the past but also pave the way for future discoveries, fostering a deeper appreciation for the wonders of the cosmos. The exploration of the CMB is an invitation to dream, to question, and to seek knowledge about the universe that surrounds us, a journey that will undoubtedly inspire generations to come. As we extend our exploration of the cosmic microwave background (CMB), it's essential to recognize how this remnant radiation serves as a crucial tool for testing fundamental theories in physics. The CMB is not merely a snapshot of the early universe. It also functions as a laboratory for examining the laws governing the cosmos. The precise measurements and intricate patterns embedded in the CMB provide opportunities to test the predictions of general relativity, quantum mechanics, and cosmological theories. One of the significant implications of studying the CMB is its relationship with dark matter and dark energy. These mysterious components are believed to comprise approximately 95% of the universe's total energy density, yet their nature remains elusive. The CMB offers indirect evidence for the existence of dark matter through the observed anisotropies. The density fluctuations that created the CMB reflect the distribution of matter in the early universe, and the presence of dark matter plays a critical role in shaping these fluctuations. The gravitational effects of dark matter influence the formation of structures in the universe, leading to the large-scale distribution of galaxies we observe today. Furthermore, the CMB provides insights into dark energy, a mysterious force driving the accelerated expansion of the universe. The data collected from the CMB can help refine measurements of the universe's expansion rate and the evolution of cosmic structures over time. Understanding the interplay between dark energy and the universe's expansion is one of the most pressing challenges in modern cosmology. The CMB serves as a vital reference point for these investigations, helping scientists piece together the complex puzzle of cosmic dynamics. In addition to testing cosmological models, the study of the CMB also plays a crucial role in our understanding of fundamental particle physics. The CMB carries information about the behavior of elementary particles in the extreme conditions that existed shortly after the Big Bang. For instance, the nature of neutrinos, particles that interact very weakly with matter, can be studied through their effects on the CMB. By analyzing the CMB's temperature fluctuations and polarization patterns, scientists can gain insights into the properties of neutrinos and their role in cosmic evolution. Moreover, the exploration of the CMB intersects with the field of quantum mechanics, particularly in the context of inflationary theory. The rapid expansion of the universe during inflation is believed to have generated quantum fluctuations, which later manifested as the temperature variations we observe in the CMB. This connection between quantum mechanics and cosmology is an exciting frontier of research. It suggests that our understanding of the universe's earliest moments may require a synthesis of quantum physics and general relativity, an endeavor that has profound implications for our comprehension of the fundamental nature of reality. As we delve deeper into the mysteries of the CMB, we also confront the limitations and challenges inherent in observational cosmology. Despite the remarkable progress made in studying the CMB, there remain uncertainties and potential biases in the data that require careful scrutiny. Factors such as foreground contamination from our own galaxy, instrumental noise, and cosmic variance can complicate the interpretation of CMB measurements. Addressing these challenges necessitates continuous advancements in observational techniques and data analysis methods, ensuring that scientists can extract the most accurate information from the CMB. One of the promising avenues for future research involves the use of next-generation telescopes and experiments designed to probe the CMB with unprecedented precision. Projects such as the Atacama Cosmology Telescope and the South Pole Telescope are already yielding valuable data, and upcoming missions like the Cosmic Microwave Background Stage 4, CMBS-4, aim to enhance our understanding even further. CMBS-4 is expected to provide detailed maps of the polarization and temperature fluctuations across the sky, allowing scientists to test various cosmological models and search for new phenomena that could reshape our understanding of the universe. Another exciting direction in CMB research is the potential discovery of primordial gravitational waves. These waves, which would be produced during the inflationary epoch, could leave distinctive signatures in the polarization of the CMB. Detecting primordial gravitational waves would not only provide strong evidence for inflation but also offer insights into the physics of the very early universe. It would represent a significant milestone in our quest to unify quantum mechanics and general relativity, and to comprehend the mechanisms that govern the birth of the universe. In addition to the scientific implications, the study of the CMB serves as a profound reminder of humanity's place in the cosmos. The CMB connects us to the universe's origins, offering a glimpse into a time when the universe was a hot, dense soup of particles. As we decipher its signals, we uncover the history of the universe and our role within it. The quest to understand the CMB is not merely an academic pursuit. It is an exploration of our cosmic heritage, inviting us to ponder the fundamental questions of existence. The stories that unfold through the study of the CMB are inherently tied to the narratives of human curiosity and ingenuity. The journey from the first observations of the CMB to the cutting-edge research of today showcases the evolution of our understanding of the universe. This narrative is rich with the contributions of countless scientists, each building upon the work of their predecessors to unravel the mysteries of the cosmos. Furthermore, the story of the CMB reflects the collaborative nature of scientific discovery. Researchers from diverse disciplines, including physics, astronomy, and engineering, come together to tackle the challenges posed by CMB research. This interdisciplinary approach fosters innovation and creativity, leading to breakthroughs that extend beyond cosmology. Technologies developed for CMB experiments often find applications in other fields, from medical imaging to telecommunications, highlighting the broader impact of fundamental research on society. As we contemplate the implications of the CMB, we also acknowledge the broader philosophical questions it raises. The study of the universe's origins invites us to reflect on the nature of knowledge itself. How do we come to understand the cosmos? What are the limits of our comprehension? These questions echo throughout the history of human thought, driving philosophers and scientists alike to seek answers that transcend individual disciplines. In this context, the CMB serves as a bridge between science and philosophy. It reminds us that the quest for knowledge is an inherently human endeavor, rooted in curiosity and wonder. The mysteries of the universe challenge us to expand our understanding, urging us to question our assumptions and explore the unknown. As we continue to probe the CMB, we engage in a dialogue with the cosmos, uncovering insights that resonate with our deepest aspirations as a species. The cosmic microwave background stands as one of the most significant discoveries in modern cosmology, offering profound insights into the universe's early moments and its subsequent evolution. As we decode its signals, we not only deepen our understanding of the cosmos but also enrich our appreciation for the intricate tapestry of existence. The CMB serves as a reminder of our shared cosmic heritage, a testament to the human spirit of inquiry and the pursuit of knowledge. The journey into the mysteries of the universe continues, inviting us to explore, question, and dream. As we advance our understanding of the CMB, we open new doors to the cosmos, revealing the extraordinary story of our universe and our place within it, a story that is far from over and one that continues to unfold with each discovery. The exploration of the cosmic microwave background is more than a scientific endeavor. It is a quest for meaning in a vast and enigmatic universe. The signals carried by the CMB connect us to the universe's infancy, allowing us to witness the echoes of creation and the processes that shape the cosmos we inhabit today. As we navigate the complexities of the universe, the CMB stands as a guiding beacon, illuminating our path and inspiring future generations of explorers and thinkers. The mysteries of the cosmos await our inquiry, and the CMB offers a glimpse into the grand narrative of existence, inviting us to become participants in the unfolding story of the universe. Continuing our exploration of the cosmic microwave background CMB, it's important to delve deeper into its implications not only for cosmology but also for our understanding of physics as a whole. The CMB has fundamentally changed how scientists view the universe, shifting paradigms and leading to new theories that enhance our comprehension of the cosmos. The journey into this remnant radiation has provided critical evidence supporting the Big Bang theory and has opened avenues for examining the properties of the universe that are not easily accessible through other means. The CMB and the structure of the universe. The CMB's significance extends beyond being a remnant of the Big Bang. It is intricately linked to the large-scale structure of the universe. The minute fluctuations in temperature observed in the CMB correspond to density variations that existed in the early universe. These variations are not just random but are influenced by the gravitational effects of matter and energy, providing the seeds for the structures that would eventually evolve into galaxies and galaxy clusters. The way these fluctuations manifest in the CMB directly correlates with how matter has clumped together over cosmic time. This relationship enables cosmologists to reconstruct a three-dimensional map of the universe's evolution. By analyzing the anisotropies in the CMB, scientists can determine how matter distributed itself in the early universe, influencing the formation of cosmic structures. This allows researchers to test models of structure formation, leading to a deeper understanding of both dark matter's role in gravitational clumping and the influence of dark energy on the expansion of the universe. Gravitational lensing and the CMB. Another fascinating aspect of the CMB is its interaction with gravitational lensing. Gravitational lensing occurs when light from distant objects is bent around massive bodies, such as galaxy clusters, between the source and the observer. The CMB is not immune to this phenomenon, and studying the lensing of CMB photons provides additional information about the distribution of matter in the universe, including dark matter. By observing the CMB, scientists can measure how light from the early universe has been distorted by the gravitational fields of intervening structures. This lensing effect reveals the presence of matter that is otherwise invisible, helping to create a more comprehensive picture of the universe's composition. Lensing measurements from the CMB can complement observations from galaxy surveys, enhancing our understanding of the interplay between matter and the universe's expansion. CMB and cosmological parameters. The study of the CMB has led to precise measurements of various cosmological parameters that define the universe's structure and evolution. Key parameters include the Hubble constant, the density of dark matter and dark energy, and the curvature of space. These measurements, derived from CMB data, have been instrumental in refining the cosmological model. One of the most significant outcomes has been the establishment of the lambda cold dark matter model, which serves as the standard model of cosmology. The lambda cold dark matter model describes a universe composed of ordinary matter, dark matter, and dark energy, with the latter represented by the cosmological constant, lambda. The success of this model in explaining a wide range of observations, from the CMB to galaxy distributions and large-scale structures, reinforces the CMB's role as a cornerstone of modern cosmology. Challenges and future prospects. Despite the wealth of knowledge gained from the CMB, numerous challenges remain. For one, there are still uncertainties regarding the precise values of key cosmological parameters, particularly the Hubble constant. Discrepancies between measurements derived from CMB observations and those obtained from local distance measurements have sparked considerable debate and intrigue in the cosmological community. This tension suggests that there may be unknown factors influencing our understanding of cosmic expansion, prompting researchers to explore potential new physics. As we look toward the future, the potential for groundbreaking discoveries in CMB research is immense. Upcoming experiments and telescopes are poised to push the boundaries of our knowledge even further. Missions like the James Webb Space Telescope, JWST, while primarily focused on infrared observations, will complement CMB research by providing detailed information about galaxy formation and evolution. Additionally, the Simons Observatory and CMB-S4 are set to enhance our capabilities in mapping the CMB with unprecedented precision, allowing us to refine measurements of the universe's early conditions and explore the nature of dark energy and dark matter in greater detail. The philosophical implications of the CMB. Beyond the scientific implications, the study of the CMB raises profound philosophical questions about our place in the universe and the nature of knowledge itself. As we uncover the intricate details of the universe's infancy, we are confronted with the realization that our existence is deeply interconnected with the cosmos. The CMB serves as a reminder that we are part of a grand narrative, a continuum that stretches back to the dawn of time. This perspective invites contemplation of the broader existential questions that have occupied humanity for centuries. The quest for knowledge through the study of the CMB reflects the human spirit's innate curiosity and desire to explore the unknown. As we delve into the mysteries of the universe, we also engage with the fundamental questions of existence, purpose, and the nature of reality. The CMB invites us to ponder our origins and the forces that have shaped our universe, fostering a deeper appreciation for the interconnectedness of all things. The role of collaboration in cosmic discovery. The exploration of the CMB is a testament to the power of collaboration in scientific discovery. Researchers from diverse backgrounds, astrophysicists, cosmologists, engineers, and data analysts, come together to tackle the complexities of CMB observations and analysis. This collaborative effort is essential for addressing the multifaceted challenges presented by the study of the universe. The success of CMB research also underscores the importance of interdisciplinary approaches. Insights from fields such as mathematics, computer science, and engineering play a crucial role in developing the technologies and methodologies needed to observe and interpret the CMB. The exchange of ideas across disciplines enriches our understanding and fosters innovation, ultimately leading to breakthroughs that push the boundaries of human knowledge. CMB research and education. Moreover, the study of the CMB offers significant educational opportunities for future generations of scientists. By engaging students in the exploration of cosmic mysteries, we inspire a new wave of inquiry and curiosity. Educational programs focused on astrophysics and cosmology can foster a sense of wonder about the universe, encouraging students to pursue careers in science and technology. Hands-on projects that involve data analysis from CMB experiments can provide valuable experience and insights into the scientific process. By equipping students with the tools and knowledge to engage with real-world research, we empower the next generation of scientists to tackle the challenges of the future. Conclusion: the ongoing quest for cosmic knowledge. In conclusion, the cosmic microwave background represents one of the most remarkable achievements in the history of science. It offers a unique glimpse into the early universe, revealing the conditions that laid the groundwork for the cosmos we inhabit today. Through the study of the CMB, we have gained profound insights into the nature of the universe, its structure, and its evolution. As we continue to unravel the mysteries of the CMB, we must also remain open to the new questions and challenges that arise. The journey into the cosmos is far from over. Rather, it is an ongoing quest for knowledge that transcends individual disciplines and invites collaboration among scientists, educators, and thinkers from diverse fields. The CMB stands as a testament to humanity's insatiable curiosity and the pursuit of understanding. It serves as a reminder that the universe is not merely a backdrop for our existence, but a dynamic entity filled with mysteries waiting to be explored. As we forge ahead into the uncharted territories of cosmic knowledge, we are inspired to dream, to question, and to seek answers to the profound mysteries that lie beyond our reach. The echoes of the Big Bang resonate through the CMB, connecting us to our origins and reminding us that we are part of a much larger story, a story that continues to unfold with each new discovery. The exploration of the cosmic microwave background is not just a scientific endeavor, it is a journey into the heart of the universe, a testament to the enduring spirit of inquiry that defines our species. As we look to the stars and the whispers of the cosmos, we embrace the adventure of discovery, knowing that every answer leads to new questions, and every mystery brings us closer to understanding our place in the grand tapestry of existence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.